Okay.
Well, welcome to the ESD Distinguished Speakers lecture series. My name is Michael Wayner. I'm not in ESD. I'm actually in the Computational Division, Computational Research Division. And it's my great pleasure to introduce Ben Santer. I first met Ben about 17 years ago during my time at the Livermore Lab. I immediately recognized him as a special talent. It was also soon clear to me that Ben is genuine, soft-spoken, yet articulate. Ben has been a tremendous influence on the way I view climate change as well as science in general. I've always been humbled to consider him as a great friend. Ben spent his teenage years in Britain and enrolled in the University of East Anglia in Norwich, England, from where he graduated with first-class honors with a Bachelor of Science degrees in Environmental Sciences in 1976. In 1983, he returned to the UEA to enroll as a doctoral student. His thesis research under Tom Wigley used Monte Carlo methods to validate climate models. Validation would become a persistent theme in Ben's research. Completing his PhD in climatology in 1987, Ben accepted a postdoctoral position at the Max Planck Institute for Meteorology in Hamburg, Germany. Professor Klaus Hasselmann, the director of the institute, suggested to Ben that the problem identifying the human-induced signal in observed pressure to climate change was an important issue. After 5 years at MPI, Ben joined the Program for Climate Model Diagnosis and Intercomparison, directed by Larry Gates at the Livermore Lab. That's where I met him. And it was there that Ben became a leader in the detection and attribution of climate change. In 1994, Ben was asked to act as the convening lead author of Chapter 8, entitled Detection of Climate Change and Attribution of Causes, for the second assessment report of the Intergovernmental Panel on Climate Change. Ben describes this experience as, quote, character building, for the conclusion of this chapter was the first definitive statement that humans were responsible for the observed increases in the Earth's surface temperature. Many entrenched interests did not want to hear such a statement and reacted in what has become a predictable pattern to this day, I'm afraid. In 1998, Ben received a fellowship from the John D. and Catherine MacArthur Foundation for his contributions to climate change research. I will never forget the look on his face when he first learned of this award. Probably best described as stunned. Do you remember that? You do remember that. In fact, Ben is a very humble man and was truly surprised. Ben's received other awards, including the Department of Energy's Ernest O. Lawrence Award and the World Meteorological Organization's Richard Gerbier Mumm Award. Each of these awards are significant in their own right. He's testified to Congress frequently, including this week, in fact. In recent years, Ben has become a passionate voice for both maintaining the integrity of climate change research as well as demanding respect for the individual scientists who perform it from the outside community. Please welcome my dear friend, Dr. Benjamin Santer.
Thank you, Mike.
Thank you.
Thank you. Good afternoon. Thank you, Mike, and I'd like to acknowledge a couple of my colleagues here in the audience who have accompanied me on this long journey through climate science. Mike, Norm Miller, Celine Bonfils, Bill Collins. What I'm going to tell you about today is not one individual's path through science, but rather the path of many people in detection and attribution, and how this particular line of research has evolved. It's appropriate to show in this first slide a picture of water vapor as observed from space. This is actually on the day that Katrina made landfall, and you can see here in column-integrated water vapor the signature of hurricanes like Katrina, typhoons out here in the Pacific. The point of including this is that fingerprinting is about pattern analysis. It's not about looking at global mean temperature alone, as I'll hope to convince you. As Mike mentioned, I've been involved with the Intergovernmental Panel on Climate Change, or IPCC, since 1990, since the first assessment report. As he also mentioned, I was the convening lead author of Chapter 8 for the second assessment report. That report came to the bottom line finding that the balance of evidence suggests a discernible human influence on global climate. I spent about 2 years of my scientific career defending that conclusion and the process by which it had been reached. Extraordinary claims demand extraordinary proof. Back then, that claim that humans were affecting global climate was extraordinary. And the way science works is an independent group of scientists in the third assessment report reevaluated the evidence and came to a much stronger conclusion than our cautious balance of evidence conclusion. They tried to quantify the size of the human effect on climate and concluded that most of the warming observed over the second half of the 20th century was due to human activities. The fourth assessment report in 2007 went one step further and used this probabilistic language. They used the word very likely, where very likely had the meaning greater than 90% probability of occurrence. So my job today is to give you some sense of the scientific underpinning for these conclusions. And also I would point out that the testimony Mike mentioned that took place just 2 days ago on Wednesday, this sentence here, and whether it was accurate, an accurate reflection of what we know about the causes of change or not, was a fundamental part of the testimony. Okay, here's the structure of what I'm going to tell you about today. First of all, I'm going to give you a brief description of the natural and human factors that affect climate, then tell you a little bit about how we as scientists study cause and effect relationships in the climate system. Climate models are our tools of the trade. They're an integral part of everything that we do. How good are they? What are their strengths and weaknesses? How do we evaluate them? I'll tell you a little bit about that. In the last couple of years, with Mike and Celine and others, I've been looking at this issue of, is it a model democracy? If you look at the entire world collection of climate models, are they all equally useful and reliable for trying to understand future climate change? I'll tell you a little bit about that, and then I want to give you some hope that the science isn't done and dusted, it isn't settled. There's still important problems left to tackle. And I think one of the key problems is this thorny one here. Can we reduce the projection uncertainties? And I think there are possible ways of doing that. Finally, I've spent a lot of my career dealing with persistent myths. And I'm going to tell you, if I have time, about 2 of those myths and how we've tried to tackle them. Well, first of all, natural and human influences on climate. One point here is that climate change is not an either-or proposition. That's something I think that the general public often doesn't understand. They think it's either all natural or it's all human. There's no middle ground. Of course, that's not the case. The reality is that the observed climate changes we've experienced over the last century and into the 21st century are due to a combination of changes in natural effects and human forcings. The natural effects include changes in the sun's energy output. The sun is a variable star. It changes on a range of different timescales. For the last 30 years, we've actually measured some of these changes in solar output. There are also massive volcanic eruptions. When they get dust up into the stratosphere, that dust can influence climate for years at a time. We're performing another natural experiment now with Mount Merapi in Indonesia, and it will be interesting to see, whether we can use that type of event as a tool for evaluating model performance. Do models get the right cooling given this volcanic forcing? Then there are things that are completely unrelated to changes in the sun and changes in volcanic dust. Internal oscillations of the climate system. We know they have a profound influence here in California. Things like El Nino and La Nina, affect temperature, affect rainfall, not only here locally, but globally. There are other modes of variability, the Pacific decadal oscillation, Atlantic multi-decadal oscillation, and scientists know and love these and study these, and again, they're internal oscillatory modes. They have nothing to do with external forcing. So all of this together constitutes the background noise against which we attempt to identify some human effect on climate. And the human effects are real. People often ask me, Dr. Santer, do you believe in global warming? Well, I believe in facts and in testing theories, and I believe in scientific evidence. This is evidence. We've measured worldwide at dozens of locations the increase in atmospheric CO2 since 1958. Before that, we measure concentrations of greenhouse gases trapped in bubbles of glacial ice. And this is our best estimate of the changes in these trace constituents over the last 2,000 years. We know from isotopic measurements, from looking at C14 and C12, that most of this rapid increase is due to the burning of fossil fuels. That's not a belief system. That's fact. We also know that in addition to changing the atmospheric concentrations of greenhouse gases, we produce aerosol particles, sulfate aerosols, carbonaceous aerosols from biomass burning. These things have profound effects on surface temperature, on the temperature of the atmosphere, depending on the chemical composition of the aerosol, the reflective properties of the aerosol. And you can see these things from space. This is the smoke from biomass burning in Guatemala and Mexico in 1998. This is not a figment of some mad scientist's imagination. And again, this issue of aerosols and their effects on climate was a prominent centerpiece of what happened on Wednesday in Congress. Humans have transformed the surface of the planet. This, too, is satellite imagery of logging roads in the Brazilian rainforest in Rondônia. When you change the surface of the Earth, when you change fluxes of moisture from the surface into the atmosphere, you change the albedo, you can have a profound influence on local, regional climate, and again, this is not a natural process here. So the difficulty and the challenge in all of this stuff is separating the natural from the non-natural. Now, it would be wonderful if we had some undisturbed Earth. We don't. But we do have computer models. We can use them to perform the Gedanken experiment that we can't do in the real world. We can just change natural factors. That's what you see here. This in black is the observed estimate of surface temperature changes over the last century. This is from the IPCC Fourth Assessment Report from the Attribution chapter. And this is essentially a result from pretty much all the world's climate models. When they were run only with our best estimates of historical changes in volcanic aerosols and the sun's energy output, you get this blue envelope here. You can't, with natural factors alone, explain the rapid warming over the second half of the 20th century. When the same models were run with a combination of human and natural factors, you get a much better match. Now, this isn't compelling statistical evidence by any means. It shows some qualitative consistency. And as I'll try and convince you, how do we go beyond this? We go beyond this by looking at complex patterns of change. That's where the real discriminatory power comes from. Okay, studying cause and effect relationships in the climate system. Again, when people ask, well, how do we know that humans are really affecting climate? It's not one individual line of evidence. I like to think that there are really 4 lines of evidence here that are important and relevant. One is we know a lot about the physical properties of greenhouse gases from lab experiments, from looking at how they behave in planetary atmospheres on other planets. We understand how they absorb and how they trap heat. Then there's circumstantial evidence. We know from computer models that if you increase greenhouse gases in the atmosphere, certain things should happen. And we see this qualitative consistency between the way the real world has actually changed in water vapor, sea level, ocean heat content, many other things, and between these climate model projections of changes. Again, that's not compelling statistical evidence. It's just another line. Then there is paleoclimate evidence, looking at the present in the context of the deep past, looking at ice core data, looking at tree ring and coral-based reconstructions of temperature changes. That, too, gives us some feel for the unusualness, if you will, of the present changes. I think one of the more powerful lines of evidence is, however, rigorous statistical comparisons of models and observations. That's where we can test hypotheses. That's where we can say, well, could it be the sun? Could it be just natural internal variability? We're often criticized, and people say incorrectly, you don't examine these alternate hypotheses. As I'll try and convince you, that's not the case. Okay, so what is fingerprinting? Well, the central tenet in fingerprinting is the different factors that influence climate, some of the different mechanisms I've shown you, the sun, volcanoes, internal variability, human-caused changes in greenhouse gases or aerosols. Each one of those things has a characteristic fingerprint. No two things do exactly the same thing to surface temperature, atmospheric temperature, and that's where the discriminatory power comes from, by trying to identify and understand the physics behind the fingerprints of different forcings. Now, in 1979, Klaus Hasselmann, whom Mike mentioned, the then director of the Max Planck Institute in Hamburg, wrote a paper, and the paper identified that this is a signal-to-noise problem, that what we're doing in trying to identify the fingerprint of a human effect on climate is searching for a coherent signal in a noisy background. And Klaus really borrowed from electrical engineering and said the signal processing techniques that we need to address this signal-to-noise problem are essentially identical to what electrical engineers developed back in the 30s and in the 40s. Again, the advantage of this type of fingerprinting, which many people now call optimal detection, because you sometimes try and enhance signal-to-noise ratios by looking for the signal in an area or in a frequency band where you think that signal is dominant relative to the noise. The advantage of this type of framework is that you can rigorously test different competitive hypotheses for the observed changes. I'll give you an example here to illustrate really the differences in the fingerprints of different forcing factors. These are all model results. These are actually calculations that were performed at BILD's former institution, the National Center for Atmospheric Research, with the parallel climate model. And what you see here are slices through the atmosphere. We're going from the North Pole to the South Pole, and from the surface right up to nearly 30 kilometers, so right up into the stratosphere. What was done here? In each case, this model, the parallel climate model, was driven by our best estimate of historical changes in solar irradiance, in volcanic aerosols, in well-mixed greenhouse gases, ozone, and this here is the direct scattering effects of sulfate aerosols. So not the effects of aerosols on cloud cover or on cloud optical properties, but just the pure scattering effect of sulfate aerosols. In each case, the model was run multiple times. I'm sure you're familiar with this. We call this realizations, starting from different initial states of the coupled system, say back in the 1880s. I think it was 1890, actually. And what you see here are the average temperature changes over the 20th century when you average over multiple realizations. And the averaging beats down the noise. The idea is to extract a better estimate of the signal, the response of the climate system to the thing that you changed in the experiment. Now, I won't go into the full details of all of these things, but what I do want to focus on here are these two fingerprints, the sun and greenhouse gases. Now, this sort of pattern here, cooling of the stratosphere, warming of the troposphere, this warming maximum in the tropical upper troposphere, we've known this since the 1960s. The first computer model experiments performed by people like Warren Washington at NCAR, Suki Manabe at GFDL showed this kind of characteristic dipole, cooling of the stratosphere, warming of the troposphere. We understand the physics very well that leads to this. You more effectively trap heat lower in the atmosphere, and the stratosphere cools. Now, the sun-only fingerprint is radically different. So our best understanding is that there's been perhaps a slight increase in solar irradiance over the 20th century that would essentially lead to more solar radiation arriving at the top of the atmosphere and heating pretty much throughout the entire atmospheric column. This fingerprint, as you'll see, even without doing any fancy statistics, is very different from the greenhouse gas fingerprint. I'd also point out, people often say models aren't falsifiable. You can never confront them with information that could be used to directly falsify them in some Popperian, Karl Popper type sense. That's not true. Back in the 1960s, when this type of experiment was being performed, we didn't have the observational data to determine whether the stratosphere was actually cooling. Satellite data come in 1979. Weather balloon data back then were sketchy at best. People like Warren Washington, who just received the National Medal of Science, incidentally, and people like Suki Manabe could have been wrong. The observations could have showed this, not this cooling of the stratosphere. But they were not wrong. As you'll see here, this was some of our earliest fingerprint work back in the mid-90s. And what we did is we looked at weather balloon data over a specific time period from the early 60s through to the late 1980s. And this showed, again, this characteristic dipole pattern, cooling of the stratosphere, warming of the troposphere, a model developed by colleagues at Livermore looking at the combined effect of CO2 changes and the scattering effects of sulfate aerosols, and sort of augmented with stratospheric ozone signal that our colleagues at GFDL had worked on, showed qualitatively similar behavior with this cooling of the stratosphere, warming of the troposphere, but obviously some pronounced differences here too, particularly over the South Polar region. But the key thing here is that the observed changes are fundamentally inconsistent with the solar fingerprint. Solar enthusiasts who argue that the sun explains everything have a difficulty, and the difficulty is the cooling of the stratosphere. Another difficulty that they face is this. This is from a report that was published last year, Global Climate Change Impacts in the United States. Mike was an integral part of that report. The bottom panel shows you the direct measurements from space of solar irradiance changes over the last 30 years. You nicely see the 11-year solar cycle, but there's been no overall increase in solar irradiance over this 30-year period. However, there has been an increase in our best estimate of global mean surface temperature over this period. So this is another difficulty. Again, if you're proposing alternate hypotheses, you have to look at all the evidence, not just the evidence that fits in with your preconceived idea of how the world should behave. Now, back in the mid-1990s, when this fingerprint work was first coming online, people were largely looking at surface temperature and atmospheric temperature. This sort of work contributed to the IPCC's balance of evidence conclusion, and it was criticized, quite rightly, I believe. People said, well, if there really is a human-caused climate change signal lurking in observations, you should see it in many different aspects of the climate system, not just in surface temperature or in atmospheric temperature. Go and convince us. Look in the oceans. Look at ocean heat content. Look at the height of the tropopause. Look at individual regions like the Arctic and Antarctic, and apply these rigorous fingerprint techniques in all of these cases. And that's what happened. Look beyond temperature. Look at atmospheric circulation. Look at zonal mean rainfall. Look at the amount of water vapor in the atmosphere. Look at things we really care about, like snowpack depth and the timing of stream flow. Look at sea ice extent, salinity. And that's indeed what's happened. Practitioners in this field of detection and attribution work have indeed interrogated many different aspects of temperature, circulation, the hydrological cycle, and the bottom line in each case is that natural causes alone cannot convincingly explain the observed changes we've seen. In my mind, at least, this substantially strengthens the case for a human effect on climate because there's internal and physical consistency to these changes. Another thing that's relevant, particularly in the aftermath of ClimateGate, where some folks have argued that all of this stuff is a house of cards built on one surface temperature data set developed at the University of East Anglia. These things are independently measured. We're talking about dozens of different observational data sets, not one data set developed at one institution. Okay. Well, another common criticism of fingerprint research is, well, it's all models. You know, you rely heavily on models, and in the words of Dick Lindzen, models are garbage in, garbage out. And another misconception is that computer models are never confronted with observations. That's not the case, as I'll try and convince you. The place that I work at Livermore, PCMDI, or the Program for Climate Model Diagnosis and Intercomparison, was set up by the US Department of Energy 20 years ago, not to develop our own climate models, but essentially to evaluate all the world's climate models, compare them with observations in a variety of different ways. Give them, if you will, hoops that they need to jump through in order to enhance our confidence in their usefulness as tools for trying to understand climate change. Here are some of the tests that we routinely do. We look at how well they simulate today's average climate, the diurnal cycle of temperature, clouds, and rainfall, the march of the seasons, response to massive volcanic eruptions like Mount Merapi or Pinatubo in the Philippines in 1991. We look at how the ocean components of these models take up tracers like bomb tritium and can make some inferences about the ventilation of the oceans by comparing tracers put into these models with the actual penetration of bomb tritium in the real-world ocean. My own personal interest is primarily focused on comparing modeled and observed changes over the last 30 years, the satellite record, and in the case of surface temperature, back to 100, 150 years. There are projects like PMIP, the Paleoclimate Model Intercomparison Program, that give atmospheric models the ice age conditions, for example, the configuration of ice sheets, the orbital parameters of the Earth at the time of the last ice age, and say, okay, given these ice age conditions, what sort of circulation do you simulate? What sort of rainfall patterns do you simulate? And then people try and compare that model output from these deep past experiments with paleo data to see whether there's some match between the two. We even look at how well climate models perform in weather forecast mode, as I'll try and show you in a minute. And we also look at how well they simulate unforced modes of variability, like El Nino. Celine has looked rather closely at the PDO recently. We routinely perform these kind of tests. I'll show you a couple examples now just to illustrate this. Now, in support of the fourth assessment report of the IPCC, the one in 2007, modeling groups in the United States and around the world performed a dozen different experiments, and they contributed all of their simulation output to PCMDI. That data was served to the entire national and international climate science community. Currently, over 4,300 scientists around the world use that CMIP3 database, as it's called. What you see here is a model evaluation exercise where we're looking at how well these models simulate the seasonal cycle. And here you see roughly 24 different variables, some of them well-known, cloud cover, rainfall, some of them a little bit more exotic. And in each case, the model and the identities of these models have been skillfully disguised with letters here. The model seasonal cycle is compared with the observed seasonal cycle. Some measure of merit is calculated, and what you see here is not an absolute measure of merit, but a relative measure of merit. So we're trying to look at which models perform better relative to their peers. I'd stress that we also routinely calculate absolute measures of merit. And if you see things in the red, then the model is 10, 20, 30, 40, 50% poorer than its peers. Things in the blue to purple, the model is doing better relative to its peers. So this particular model here, model L, across the board pretty much is doing rather poorly relative to its peers. Another model, model G, is doing rather well compared to its peers. One of the curious findings in this type of work is that when you average all the model results and calculate either the model mean or model median, that model average or median often outperforms individual models. Now, I use the word often advisedly because there are instances, particularly when you're looking at trend behavior, where the model average does not outperform individual models, and where what you put in the transient experiment, the forcings that you use, are crucial to the goodness of fit relative to the observations. But here, for the mean state at least, for the mean seasonal cycle, this model average better than individual models holds. Yes, sir, you had a question.
I was just curious, I'm confused. In this comparison, are you comparing the individual model to the mean of the models, or you compare the individual model to the data?
Sure, let me explain again. So we're looking here over the seasonal cycle, and we're looking at climatological averages over the seasonal cycle. We're comparing each model, so A through to V, for each field to a companion observational field and calculating some figure of merit there. And then what we do is we calculate the relative skills, so how well each of these models is doing relative to its peers, relative to actually the median model. Now in this thing, what you're actually doing is you take the data at each grid point for each field here, for each one of these models, and you average it, or you calculate the median, and then you compare that median model with observations. And then you can see how well the median model does, in a relative sense, to each of these roughly 24 individual models. Does that make things? Okay, I'd be happy to explain in more detail later. I should point out that this is something we see in numerical weather forecasting as well, that when people average results from multiple weather forecast models, they often get a better skill than when they use one model alone and perform many realizations of a forecast with that one individual model. And we think we understand some of the reasons for the superiority of the multi-model average. Some, but not all of the reasons for the superiority. As I mentioned, we also use now increasingly weather forecast techniques. So I'll give you one example of this here. Many of you may be familiar with these ARM sites, these atmospheric radiation measurement sites that are established around the world. They make very high-resolution measurements of atmospheric radiation, clouds, temperature, that one can use to confront climate models with. Now, this is a result from Point Barrow in Alaska, and it shows over one particular month here cloud fraction, and you can see low-level cloud here. You can see storm fronts coming through over this month. And one particular model, again, the Community Atmospheric Model, version 3, developed at NCAR, was used in weather forecast mode. So it's trying to simulate this month and actually ingesting satellite information and other observational data And you can see then when you compare with the arm measurements that the model does get this low-level cloud, but it doesn't get enough. It gets some of the structure of these fronts. The interesting thing about this approach is that you very quickly see errors manifest themselves. And these errors have signatures when you run the same models in climate mode. So the idea is that in this parameterization test bed, as people call it, you can change individual parameterizations and very quickly see what their impact is on the solution and whether you improve the physics and get an improved match to high-quality observations or not. It's going to be a powerful tool for error diagnosis, for actually figuring out the causes of errors in models. Okay, so I hope I've convinced you now that when people tell you models are never confronted with observations, that's not the case. We have a variety of ways of doing that comparison process. How about this issue of discriminating between these two models, trying to identify better, worse models? Is there any scientifically valid way of doing that? Well, as I've showed you, not all models are of equal quality. And because of differences in model quality, people for probably around the last 5-6 years have tried to weight projections of future climate change based on some estimates of how well models capture important features of today's climate. And most of that weighting has just looked at the mean state, how well models simulate the current average climate. So the question is it a model democracy? Should we pay equal attention to the results from each model? Should we weight? If so, how should we weight? And does it matter if you do some weighting or screening? Do you get a different result than in the model democracy case? And can we define in some Letterman-type sense the top 10 climate models? Okay, well, we looked at this a year ago. We had published a paper in 2007 where we claimed to have identified a human effect on the pattern of atmospheric moisture changes over the ocean. And that work was criticized, quite rightly, I think, because we did a model democracy. We used all the models in the CMIP3 archive, but we did not attempt any kind of weighting whatsoever. We treated them equally, as if their estimates of the signal, the response of water vapor to greenhouse gas changes, were of equal quality, and their estimates of the noise of natural climate variability were also of equal quality. And people said, well, okay, what happens if you don't do that model democracy, if you try and repeat your fingerprint analysis with water vapor, but with the top 10 models? So that's what we tried to do here. And what we did is we looked first at 20 different metrics of how well all of these models, the CMIP3 models, simulated the mean state and the seasonal cycle of water vapor and of ocean surface temperature over a number of regions around the globe. And then what you can do is you can take these 20 metrics and you can rank the models 1 through 22, and you can rank them either parametrically or non-parametrically. And this gray box is where you want to be. This defines the top 10 models. We also did this not looking at the mean state and the seasonal cycle, but looking at a more challenging standard, if you will. We looked at how well these models simulated the observed patterns of water vapor and sea surface temperature variability in different regions and on different time scales. By different regions, we looked at things like El Nino regions, Pacific decadal oscillation, Atlantic multi-decadal oscillation regions, the tropics. Time scales, we looked at month-to-month variability, year-to-year, and decade-to-decade variability. In total, there were 50 metrics in this case here. Now, what I want to show you is, look what happens to the top 4 models here when we look at model fidelity in simulating the mean state and the seasonal cycle. They're an American model, a Japanese, a British, and a German model. When you look at where those 4 models wind up in simulation of variability statistics, none of them really are in the top 10. The point here is a simple one, that model errors are complex in space and time. And the idea that one statistical attribute of model performance fully describes the complexity of model error structures is wrong. I think at this stage of the game, what you want to do, and what we did then, is we looked at whether this made any difference to stuff we cared about. We took different sets of top 10 and bottom 10 models. So, for example, the solid bars are top 10 models. The hatch bars are bottom 10 models. The N's here means the non-parametric ranking. The P's mean parametric ranking. The colors mean these are detection studies carried out with a ranking based only on the seasonal cycle or only on the variability metrics. And the green is all 20 plus 50, all 70 metrics used for ranking the models. The key thing here is that we could always identify some anthropogenic signal in observed water vapor changes, regardless of how we cut the cake, regardless of which set of 10 models we selected out of these 22, and that's because the physics was simple. It's basically Clausius-Clapeyron here, dictating the response of water vapor to anthropogenic forcing, and the dominant mode of natural variability, which is an ENSO-like mode, looks very different from the fingerprint of water vapor response to anthropogenic forcing. So, of course, this isn't a general result that would hold for all regions or all variables, but for water vapor at global scales, the physics was simple, and that's why the ranking and the model selection and weighting didn't really matter. We have our own local signal-to-noise problem. Okay. Can we reduce uncertainties in projections of future climate change? A key issue for everyone in the room, I think. I'm sure you're all familiar with this figure, one of the most famous figures from the fourth assessment report of the IPCC. It shows projections of surface temperature change under different storylines, if you will, different estimates of population growth, of collaboration between countries, of technological development, different mixes of energy use. And basically this bar here shows you the scenario uncertainty, if you will. This bar here shows you that for any individual scenario, like this is the A2 sort of business as usual type scenario, there's a very large range of uncertainty that arises from inherent uncertainties in the model physics and feedbacks. And in this case, for A2, that uncertainty is large, from 2 degrees Celsius temperature increase out to 2100 to over 5 degrees. How do we shrink that? Is there any way that we can, as scientists, reduce this uncertainty, which really we've lived with for the last 20, 25, 30 years? Yes? Right. That's why it's really important to try and understand how and whether we can reduce these uncertainties, because I think they do drive the relative mix of adaptation and mitigation strategies that you might choose. I mean, if you're down here, some people would say, well, we can possibly adapt our way out of things. If you're up here, then you can't. Adaptation clearly is not going to be a sufficient strategy for dealing with that magnitude of change. So this is important. You know, this is the future for all of us. Are there ways of reducing these projection uncertainties? Well, first of all, why? Why is it difficult to reduce them? In weather forecasting, of course, we have observations. We make a forecast, we confront it with observations, and we assess the model skill. In climate change experiments, we're making projections decades or centuries out into the future. We have limited data available for assessing the skill of the forecast. And the real difficulty is in figuring out the relationship between things we can measure in the real world now and projections of future climate change. Is there a relationship between current day observables and projection uncertainties? Yes?
Since you
That's a good point. No, I think it does not necessarily mean that if you're good in weather forecasting, you're good in climate projections. You know, there are assumptions there. One is that the feedbacks that you look at, some of them are long timescale feedbacks, like feedbacks associated with the carbon cycle. Clearly, if you're looking at weather forecasts, you're not really evaluating how faithfully the models capture those longer timescale carbon cycle feedbacks. So I agree with you. However, I would say that some of the errors that we see manifesting themselves in climate models, for example, with regard to the simulation of precipitation, you can see the fingerprints, the precursors of those errors when you run the climate models in weather forecast mode. They set up very rapidly. And that gives you the opportunity to do real diagnosis of the causes of those errors. You can very quickly make changes to the physics or parameterizations and get some feel for whether the changes truly give you a better physical simulation. Does that make sense? Well, again, it's sort of like a necessary but not sufficient condition. If you do well on weather forecast timescales, you've got to get a lot of important physics right. But that does not guarantee, as I pointed out with the carbon cycle feedback case, that you're necessarily going to get all the feedbacks right on the long timescales. And some of those drive that projection uncertainty that I showed you. Yes? Yeah, perhaps we could defer that to later, to a little later, and actually we have one of the world's experts on that in the room here. I'm getting into the feedback issue right now. As you see here, this is a beautiful piece of work. It was done by Alex Hall and a colleague 4 years ago, and what they did is they looked at one of these feedbacks. We understand that these projection uncertainties are largely associated with uncertainties in the portrayal of feedbacks in climate models. And the main uncertainty is in the portrayal of feedbacks in clouds, but there are also uncertainties in the water vapor feedback, snow, and ice albedo feedbacks. What Alex Hall and his colleague looked at was uncertainty in the snow feedback. They looked at satellite-based measurements of northern hemisphere snow cover, and they looked at temperature changes in the northern hemisphere between April and May. And what you see here, again, these are roughly the 24 IPCC CMIP3 models. They looked at the April to May temperature changes and at the April to May snow cover changes on seasonal timescales. Okay, so you can plot each model there. But you also have, for each model, the climate change experiment. So you can look over the 21st century at the temperature changes and the snow cover changes. And the nice thing here is there was almost a beautiful linear relationship between the two. Now here, on the short seasonal timescale, we've got good observations. We can reliably pin down the April to May snow cover changes, the April to May northern hemisphere temperature changes. And here's the uncertainty. This gray bar marks sort of the observational uncertainty in this covariance relationship between April to May temperature and April to May snow cover. And the implication is that models that lie far away from this gray band probably are not realistic in terms of their portrayal of this feedback mechanism. Now this is nice because it offers the possibility of using short-term observations to constrain this, the long-term uncertainty in the feedback. You see some models are too sensitive, some models aren't sensitive enough, and if you find these sort of timescale invariant relationships, then maybe, just maybe, you can use high-quality short-term observations to shrink the uncertainty in the thing you care about. Can we do this for other things? We've been looking at this for water vapor, and what you see here is a similar sort of thing. Again, these are the CMIP3 models, and what you're looking at now is not just two time scales, which was what Alex Hall was looking at, the seasonal time scale and the century time scale. We digitally filtered the data, and we're looking at 4 different time scales: monthly variability, annual variability, decadal, and then this is the century time scale change, in this case over the 20th century. So what do you see here? On the bottom, you see sea surface temperature in the tropics, and this is precipitable water in the tropics. And the nice thing about this is that to first order, look at the slope of this line. It's very similar to within 10%, and the positions of models on this line are quite similar too. Again, the idea is that there's some relationship between the short time scale variability of this relationship, which we can measure really well, you know, the monthly and annual time scale stuff, and the long time scale behavior of this proxy, if you will, for the water vapor feedback. Now, this isn't a direct measure of the water vapor feedback, but it shows you that something that is directly related to the water vapor feedback, the response of column water vapor to ocean surface temperature changes, is, to first order at least, relatively timescale invariant. So I think that's where a lot of research is currently being directed, looking at feedbacks. Can we go beyond these broad brush statistical metrics of model performance and develop things like this, you know, that Alex Hall looked at, or things that enable us to look at other feedbacks and maybe constrain their long timescale uncertainty? That's the challenge for all of us in the room. Okay, just finally here, mythology 101. I've spent a lot of my career dealing with various myths out there. One myth was that the troposphere was cooling, that satellite-based estimates of temperature change showed a cooling troposphere, and that this invalidated surface-based estimates of warming and also invalidated all climate models, which suggested, as I've showed you, that the troposphere should warm in response to human-caused increases in greenhouse gases. This was a report published by Fred Singer in 2008, a so-called Heartland Institute report. This was the title, Nature, Not Human Activity Rules the Climate. The report was formatted to look exactly like an IPCC report, but it was called NIPCC, Non-Governmental International Panel on Climate Change. Well, one of the cornerstones of this NIPCC report was a paper by David Douglas et al. The et al. Also included Fred Singer and John Christie. And this paper had been published in 2007 and claimed that there was some fundamental disconnect between modeled and observed temperature changes in the troposphere. And Dr. Singer wrote that the Douglas et al. Findings constituted an inconvenient truth and proved that nature rules the climate. Human-produced greenhouse gases are not responsible for global warming. I talked about this a little earlier this year at the Berkeley Law School, and it turns out that the centerpiece of that NIPCC report, the Douglas et al. Paper, had devised a statistical test to compare models and observations, and the test was wrong. When you applied the test to randomly generated data and increased the sample size, so effectively the number of models, you can think of this as the number of models using to do this test. Again, randomly generated data where you know a priori that the only differences between these random samples should be due to chance alone. In the end, asymptotically, this model rejected the hypothesis that there was no significant difference between the random samples 4 times out of 5. And even, you know, at the sort of CMIP3 type sample size of 24 models here, 3 times out of 5, well, any test that fails with random data isn't going to give you reliable results. And you would think that before shattering the world of science and concluding that nature rules the climate, that you would make sure that you do your statistics right. These gentlemen did not do that. Okay, recently, back in May, I testified in front of the House Select Committee on Energy Independence and Global Warming, And one of the witnesses, Professor Will Happer, who I believe has been here at Berkeley recently, had this statement in his written testimony. And of course, we've all heard about this claim recently that there's been no statistically significant warming post-1988, post the big El Nino event in 1998. Professor Happer actually said this: over the past 10 years, there has been no statistically, I think he meant to say significant, global warming. This is not at all what was predicted by the IPCC computer models. So let's look at that thesis. Now, I've decided to do this with tropospheric temperature rather than surface temperature. For the satellite-based estimates of tropospheric temperature change, we have near global coverage. We don't get into all these issues about the quality of the surface temperature data sets. It's instructive to do it with tropospheric temperature. And these are satellite-based estimates of the global scale changes in lower tropospheric temperature since the beginning of the satellite record in 1979. And what you can see is, wow, a lot of noise. That doesn't surprise us. There's some overall warming trend, but on the 10-year time scale, these are all 10-year trends fitted to overlapping segments of the data, where the overlap is by 9 years. Okay? So there are 22 individual 10-year overlapping trends on this figure. And what you can see, this is the period that commentators have focused on, this post-1998 period. There's not a lot of warming over that period, but notice that even in the context of the observations themselves, the statistically most unusual 10-year period is this here, not anything post-1998. So the message is clear again. There's a lot of noise in the climate system on 10-year timescales. El Niños, La Niñas, volcanic eruptions. This is El Chichon. This is Pinatubo here. They influence these short timescale trends. When you look on longer timescales, of course, you beat down the noise substantially. This is doing the same exercise with the same data, but now fitting overlapping 20-year trends. And here, the range is from minus 0.1 to plus 0.4. You've shrunk that range by a factor of 4 by looking at a longer time scale and beating down the noise. Again, this is well known in the scientific community. Every practitioner of fingerprint studies would not look on 10-year time scales for an anthropogenic signal. The noise kills you. Not only does speed kill, noise kills as well. So examining Professor Happer's statement again, what you can do is you can look at all of these climate model simulations of 20th century climate change, and we've actually spliced them together, since most of these simulations of 20th century climate change end in 99 or 2000. You can splice them together with a business as usual scenario run, the SRES A1B run. So you can look at the same period in the climate model output as in observations, 1979 to 2009, the length of the satellite record. Okay, and you can do the same fitting of overlapping 10-year trends to the model output, and that's the sampling distribution that you see here. It's output from 19 different models. There are 50 different realizations of extended 20th century climate change. It's over 1,100 samples of 10-year forced trends. Now, you can easily see, again, without any fancy statistics here, that it's easily possible on the 10-year time scale to get trends that are 0 or even negative. No big surprise. In the model world, like in the real world, natural variability is large and influences these short time scale trends. And if you add the observational results to this, these are the observational trends from both the Santa Rosa group, remote sensing systems, and from John Christie and Roy Spencer at the University of Alabama. Now, these vertical lines are the averages of those 22 individual overlapping trends. And you can see when you don't focus on one individual trend, but the average 10-year trend, well, there's nothing unusual. Nothing unusual at all. And it's easily possible, And this is the 5 to 95 percentile range. Again, it's easily possible for models to simulate the observed behavior on the 10-year timescale. Professor Happer testified about this issue. He cited nothing in support of his written testimony. The scientific evidence does not support that statement. Okay, just finally, I hope I showed you that we've identified human fingerprints in many aspects of the climate system. We've gone beyond that early work where we just looked at surface temperature. We've looked in the cryosphere at Arctic sea ice extent. We've looked at surface pressure patterns, ocean heat content, changes in zonal mean rainfall, the height of the tropopause. People are doing this kind of fingerprint detection on a regional basis. And the bottom line, the red thread running through all of this is natural explanations alone are not convincing. They do not fit the observational data. Despite claims to the contrary, we routinely confront computer models with observations. As I've showed you, we do that in a variety of different ways. That gives us some confidence in the ability of these models, not only to simulate today's average climate, but also the march of the seasons, aspects of variability. And this is what we have to continue doing in future to enhance our own and the public's confidence in the usefulness of these things as tools for trying to understand future climate change. I've also showed you that model errors are complex. If you're trying to identify the top 10 models, it's not an easy job. I don't think there's any scientifically defensible way of claiming that you can come up with one metric to rule them all, one measure of model performance that summarizes every aspect of model errors. My feeling is that at this stage of what we do, it's about sensitivity. You do model weighting or model ranking in many different ways, and you see whether what you really care about, like our ability to detect anthropogenic climate change, is sensitive to different ways of doing the weighting. I've also showed you that the science is not done and dusted. There are important uncertainties left for all of us to look at, and I think the main one for me is shrinking the projection uncertainties. Just finally, in the last year, there's been much discussion of trust and accountability in climate science. Some witnesses in their congressional testimony have argued that climate modeling is some shadowy, secretive endeavor. That is not the case. As I mentioned, we have things like the Earth System Grid that enable our community to share climate model output, observations, visualization, and analysis software. We have these large multi-model archives that are currently being used, like CMIP3, by 4,300 scientists around the world. That is not shadowy. That is not secretive. In my opinion, climate science is a model for how data should be shared in many other scientific branches. Yes? Bill, do you want to respond to that question before you leave? Thank you. You've all heard about ClimateGate. Some have argued that ClimateGate calls into question every conclusion I've presented to you today. There have been over 5 investigations now of the scientists involved in ClimateGate. These investigations have come to the conclusion that nothing in those over 1,000 stolen emails calls into question the finding that the Earth is warming and that human activities have significantly contributed to this warming. Finally, Some of our elected representatives have opined that climate science is a scam, a hoax, a conspiracy. It is not. Government and industry, in my opinion, need to make decisions on what to do about climate change on the basis of the best available scientific information, not misinformation, disinformation, or wishful thinking. We simply can't embrace ignorance. We don't have that luxury. Thank you very much. Yes, sir.
A policy question. You know, I may not believe in rain, but when I step outside, I'm going to get wet. And is there any kind of consensus that even if we argue about whether it's man-made or not, that there is a warming trend occurring, and therefore things need to be prepared for that warming trend?
Well, the IPCC fourth assessment report used the word unambiguous to describe the warming of planet Earth. That's a fairly strong word. I think that when you get over 2,500 scientists to agree to use a word like that, it's a pretty clear case. And again, that evidence comes not purely from surface temperature data sets developed at the University of East Anglia and elsewhere, comes from measurements of ocean heat content changes, measurements of changes in water vapor. There's an internal and physical consistency to the changes that we see. So warming.
Well, I mean on policy, but kind of behind the scenes, they ask you these questions in public. Like the Army Corps of Engineers is dealing with sea level, they don't call it climate change, but they're preparing for this sea level. Do you have a sense that policymakers are actually doing responses, even if there's this sort of...
Well, I have a sense now, particularly after Wednesday's testimony, that people, regardless of their political affiliation, recognize that this is happening. There may be debate about the size of the human effect on climate. There may be some ideological divides in terms of that question of the magnitude of the human effect on climate. But most rational people recognize that this is happening, and this is something we're going to have to deal with. And dealing with it also makes sense in terms of energy independence, in terms of national security, in terms of transition to a clean energy future for the United States. As many pundits have pointed out, there are tremendous co-benefits to doing something about climate change. So I think there are plenty of policy drivers out there independent of the science. My own perspective is the science is compelling and credible. And we should not forget that, and we have the responsibility of trying to articulate the scientific evidence all the time.
You hinted about the discussion on Wednesday a number of times how important it was different than what it might have been expected.
Sure. Well, Wednesday's testimony was in front of the House Committee on Science and Technology, and it was historic. The House Science and Technology Committee had 3 panels back-to-back. The first panel was on the science of the greenhouse effect. The second panel was on this sort of information, the evidence basis for human effects on climate. And the third panel was on global and regional impacts of climate change. There were 12 witnesses, 9 from the majority side, 3 from the minority side. And the chairman of the House Committee on Science and Technology, Chairman Baird, at the outset said, this is historic. I want to have the science on the record. I want our children and grandchildren to be able to read this record in 20, 30, 40 years' time. I want them to see the video of this day, and I want them to decide who faithfully represented the science and who did not. So it really felt historic. They had to bring in additional chairs in order to seat people in the room. It was open to the public. It was well attended both by Democratic and Republican members of the Science and Technology Committee. And on our panel, much of the debate was about that IPCC statement that I read to you in the second slide. Most of the warming observed over the second half of the 20th century is very likely due to human-caused changes in greenhouse gases. Now, the minority side witness, Professor Pat Michaels, argued that he had done an analysis that overturned that finding, that he had single-handedly demonstrated that that finding was incorrect. His analysis went sort of like this. He looked at observed surface temperature changes over the last 60 years, from 1950 through to 2010. Our best estimate from the surface temperature data that I showed you is that the warming over that 60-year period, the total linear change, when you fit a linear trend to those 60 years of surface temperature data, is roughly 0.7 degrees Celsius. Then Professor Michael said, well, I can identify 4 things that are completely unrelated to CO2 that I am going to subtract from that 0.7 degrees. Those 4 things were errors in ocean surface temperature data, changes in stratospheric water vapor, economic activity, and changes in black carbon aerosols. And in his estimation, and this was from a survey of the literature, the total effect of those 4 factors was to warm, and the total effect was 0.4 Celsius over 1950 to 2010. So he subtracts 0.4 from 0.7 and gets 0.3. And he says, aha, 0.3 is less than half of 0.7. And the IPCC said that most of, i.e. more than half, of the observed warming was due to human-caused changes in greenhouse gases. But I only have 0.3 left. And even if that 0.3 is all due to human-caused changes in greenhouse gases, it's less than half. So I single-handedly have overturned orthodoxy. What was wrong with that analysis? What was wrong with that? Well, a number of things were wrong. One thing that was wrong was there were no error bars. So his estimates of the things to be removed that were unrelated to CO2, these 4 factors, his estimates of those things were given to 1,000th of a degree C with no error bars. And in at least 2 of the cases, the stratospheric water vapor case, that was based on a paper by Susan Solomon, you may be familiar with. Susan looked at water vapor changes in the stratosphere from 1980 through to 2010. 1988 to 2000, stratospheric water vapor increases. 2000 to 2010, stratospheric water vapor decreases. Professor Michaels somehow used that to apply to the 60-year period, 1950 through to 2010. You can't do that. The main flaw, getting over the non-existent error bars, getting over giving things to 3 significant figures, getting over the fact that you can't do what he did with water vapor and economic activity, is he forgot cooling influences on climate. So, of course, the IPCC and others have studied the effects of sulfate aerosols on climate for over 20 years. Both the direct scattering effects, so how aerosol particles reflect some fraction of incoming sunlight back into space, as well as the indirect effects of aerosols on cloud brightness and on cloud cover. Now, the direct scattering effect is much better known than the indirect effect. The IPCC in the 4th assessment report concluded that the direct scattering effect was negative, so a cooling, and probably of order minus 0.5 watts per square meter with some uncertainty band on it. The indirect effect was estimated as 0 to minus 2 watts per square meter. Very large uncertainty range, but also negative. Professor Michaels didn't even mention sulfate aerosols. Now, if you look at what other people have done, they've tried to estimate the sulfate aerosol cooling over the last 60 years. You know, the best estimate is that that cooling ranges, say, from 0.3 to 0.5, so a cooling of 0.3 to 0.5. Now, let's assume that it's only 0.4 in the middle of the 2, minus 0.4. And then you assume Pat Michaels was perfectly right with the 4 things that he removed, that 0.4 estimate from the warming effect of the 4 factors he considered is perfect. You go from minus 0.4, you add plus 0.4, you get 0. You've still got to get to 0.7. Okay, so could it be the sun? No. The sun couldn't explain that increase in 0.7. If it did, we'd expect to see huge solar cycles every 11 years in the surface temperature data. We don't see that. It's not volcanoes. There's no mode of natural variability we know that can do a thing like that. What the IPCC actually concluded was that because of sulfate-induced cooling, the best estimate of the greenhouse gas component was actually larger than the observed warming. There's been this offsetting effect. You have cooling and warming influences. Another problem with Professor Michael's analysis was that he posits that one class of aerosols, black carbon aerosols, have an effect on climate, and another class of aerosols that cause cooling aren't even mentioned. You can't do that. This analysis was wrong, and anyone, again, who claims that they're overturning the fundamental conclusion of an assessment report better do it right, better do it thoroughly, better do it carefully, and he did not do that. Yes, I challenged him on that, and there was some back and forth between us. And I pointed out that the analysis was wrong and should never have been presented to Congress.
Could you say something about the application of climate models to paleoclimate, especially periods with larger CO2 in the atmosphere?
Gee, it's a shame that Bill Collins has left the building like Elvis, because people routinely try and use climate models to simulate periods in the past. I mentioned this PMIP program, Paleoclimate Model Intercomparison Project, where people tried to simulate the climate of the last ice age. But others, like Jeff Keel, have gone much further back in time and have tried to simulate climates with much higher CO2 levels than today. I'm not really an expert on that issue. I'm sure some of the people in the room are. But I think one answer to your question is that given the increase in computational power, people are now trying to use models to simulate not only the last 150 years, but the last several thousand years. And I think over the course of the next 10 years or so, people are going to use these models to try and simulate full ice age cycles and see whether they can grow and remove ice sheets in response to what we know about changes in Earth's orbital parameters, eccentricity, obliquity, and precession. So it's a rich field of endeavor, and computational power will help us to use these models to simulate the deep past much better than we do at the present. Yes?
So some of my colleagues are involved in graphical processing-based computations, Falcon processors or Intergovernmental cards. So what sort of impact does that have on our models? It's surprising that the old models are predicting the same thing as the models are, yet the new models should be so much better in terms of granularity and
Yeah, well, the granularity is much better, and Mike here and folks at Berkeley have looked at these issues of what resolution buys you. Mike has looked at this issue in terms of hurricanes. For things like hurricanes, it's huge. You go to higher resolution, your ability to represent rain bands and the central pressure in the eye of the hurricane is immensely improved relative to coarse resolution models. There are other things, however, where resolution doesn't buy you a lot. And some of the results I showed today, actually there were two cases where there were pairs of models. A Japanese MIROC model and a Canadian Climate Center model had provided a lower resolution and a higher resolution version of their model to this CMIP3 archive. And interestingly, the higher resolution model didn't do well across the board relative to its lower resolution peer. And we understand some of the reasons for that. If you're looking over areas where orography is important, like the Sierras and the Alps, resolution buys you a lot, but it doesn't necessarily buy you a lot when you look in regions where orography is not that important and where errors in the physics and dynamics of the model really drive the solution. Yes.
The question is not much related with models, and I've seen that very recently the World Energy Outlook for this year was released, and in there they discuss about the limit of temperature increase in the century, and so they discuss about the threshold that was widely they chosen. Some time ago it was 2 degrees. And they actually shifted to the more easily achievable and likely limit of 3.5 degrees for a concentration in the atmosphere of 600 parts per million. Now, I'm not a climate scientist, but I think that, 3.5 degrees is quite high temperature. I'd like to know what you have any comment.
Well, thank you for that question. This relates to the issue of dangerous anthropogenic interference. So at what level of temperature increase do we risk really bad things happening to the climate system, like complete loss of the Greenland ice sheet? And right, the European community decided a few years ago that 2 degrees was their limit for dangerous anthropogenic interference. It's worth noting that that decision is not purely a scientific decision. A lot of value judgment comes into that. We don't know in reality where that dangerous anthropogenic interference limit lies. We don't know how close we are to some of these tipping points in the climate system. So defining those thresholds beyond which really bad things could happen is a tremendously difficult endeavor, in my opinion.
We have time for one more question. Is there any consistency in the global models about whether frequency of El Nino is
I think the answer is no. Model projections of future changes in El Nino frequency and in intensity, the statistics of ENSO, there are a lot of intermodel differences in there. There is some similarity in some aspects of their projections of El Nino changes, but I don't think really in terms of the frequency, nothing that I would bet the farm on. Yeah. Well, thank you. The point I tried to make on Wednesday in Congress is that uncertainty is an integral part of our scientific lives. As I've tried to show you, when we do fingerprinting now, we routinely look at model-based uncertainties in estimates of the fingerprint we look for, model-based uncertainties in the noise of natural climate variability. We look at uncertainties in the statistical methods we apply to compare models and observations. We couldn't get papers published if we did not fairly and comprehensively look at the impact of uncertainties on our ability to identify human fingerprints on climate. The concern is the asymmetry. The type of analysis I've described that was presented to Congress by Professor Michaels had no uncertainties. It had no error bars. It had estimated changes given to 1,000th of a degree C, and that's not permissible. That's not a rational way of dealing with uncertainties. So one would hope that if you're skeptical about these kind of things that I've talked about today, that any analysis would embrace uncertainties in the same way as the detection and attribution community has tried to do.
Let's thank Ben. That's great. Oh, Ben's going to be here for a while, right?
Yeah, Ben's going to
be meeting with a bunch of people, but they know
They know who it is.